In this final video on gravitational fields and potential, we'll look at a graph of potential against distance. So I'll put the title potential gravitational. Okay, so that's the title. Now, typical graph you'll see in a question, an IB style question, you will have on the y-axis, you have that going down like that, and on the x-axis drawn like that. And here is the potential, the gravitational potential, and here is the distance from the center of the planet, r. So the gravitational potential is in units of, will be in units of multiples or just as a joules per kilogram, and the distance, let's keep it in meters. Okay, now, so what we'll find also in the graph, you'll see a point that represents the where the surface of the Earth starts, and we'll represent that by this distance there from the center of the Earth to the surface. So if I draw a little picture here of the Earth, we see that, and draw a line like that. That point there will be a distance r from the center, and where it hits the surface, that's the center, it'll be denoted by what could be denoted by big R. Okay, so, and I'll draw this line here because we don't get into potentials in the center of the Earth, and so therefore we could have a line that approaches, for instance, say starts here and approaches infinity. Okay, now this here would be the potential of 0, so that would never actually touch that line, so you'd never actually get 0 potential, well, only at infinity, which is not going to happen in a hurry, but the potentials do touch there, and that is where at the surface, but we stop there. Okay. Now, what does this show you? So let's take 2 points. So if we've got a point here, let's take a point here, A. At that point there, A will be a certain distance from the center of the Earth, and if you knew what that distance there, you could join it up, and that will give you the potential at that point there. And then take another point here, say B, and again at a certain distance, and at a certain distance away it would tell you the potential. And of course the distance between A and B, between there, would be the change in potential between A and B, and if you wanted to find the change in potential energy, you'd have the change in potential energy, or the energy lost or gained or transferred between A and B, would be energy potential equals the change in potential times the mass of the object. Often it's a satellite or rocket or whatever. Okay. Now another thing to look at here is, okay, what else do we know about this? Well, another thing interesting about this is the gradient. Now let's take a point P on this curve, and if we drew a tangent, okay, and draw a nice big triangle, we'd find the gradient at that point P, and the gradient is equal to the gravitational field strength. So the gravitational field strength is represented by, is equal to the change in V over change in R, which can be written as, without using calculus, change like that over r like that. Now it has a negative in front of it, but I won't be bothered about that. Or if you think about calculus as the change in r tends towards 0, you get the gravity is equal to dVdr, and it's negative, but again I wouldn't be hung up by that. So basically the gravitational field is the change in potential with respect to the change in distance, and the steeper the line, the greater the gravitational field. And that is that. So in fact, to carry on that, if you were to calculate the gradient just as it hits the surface of the planet, in fact with the Earth, you would find that G would be equal to change in V over change in R, or the calculus version, which would equal to about 9.8 newtons per kilogram, or meters per second to minus 2 there.